In this lecture, we're going to look at the question of how stars form. The Sun is a 4.6 billion year old main sequence star, and it is in equilibrium. It is in hydrostatic equilibrium, in which the internal gas pressure is balanced by the self-gravity of the Sun. It is in thermal equilibrium, in which the amount of energy being generated by nuclear fusion in the core exactly balances the loss of energy due to luminosity at the surface of the Sun. It is powered by hydrogen fusion into helium in its core. This is how it is today, but how did it get this way? The birth of a star is a three-stage process. The first stage, called the protostar phase, is where the protostar, the growing star, builds up its mass slowly by the process of accretion until it eventually establishes a state of hydrostatic equilibrium. The second phase is the pre-main sequence phase, in which it gets all of its energy from gravitational contraction through the Kelvin-Helmholtz mechanism, and while it is in hydrostatic equilibrium, it is not yet in thermal equilibrium. It is, however, slowly establishing thermal equilibrium as it goes through the phase. Finally, the zero-age main sequence is when the star begins to burn hydrogen into helium through fusion in its core, and it achieves both hydrostatic and thermal equilibrium. Let's go through all of its phases, from the earliest phases up to the point that the star becomes a zero-age main sequence star. The raw material for forming stars is provided by giant molecular clouds, what we're going to call GMCs for short. These are massive cold interstellar clouds composed primarily of molecular hydrogen. This is two hydrogen atoms combined together to form an H2 molecule. We see these in space as very dark, very dense clouds. The properties of these are that they have sizes between 5 and 200 parsecs, masses that range anywhere from 1,000 up to 10 million times the mass of the Sun, but are very cold. The temperatures in these gas clouds, measured from the motions of the atoms and molecules in the cloud, are only between 10 and 30 degrees Kelvin, 10 or 30 degrees above absolute zero. The densities are anywhere from 100,000 to 10,000 to a million atoms per cubic centimeter. In astrophysics, we call this high density when we're talking about interstellar material, but a density of 10 to the 4 to 10 to the 6 atoms per cubic centimeter is actually a harder vacuum than we can achieve in all but the most extreme vacuum laboratories. Funny in the way we have to rescale our ideas of big, small, high, and low when we talk about different places in the universe. These giant molecular clouds are supported almost entirely by a combination of internal gas pressure, weak magnetic fields, and bulk motion of the gas. You shouldn't think of these things as standalone clouds simply being supported by pressure. They're also threaded by weak magnetic fields, and the gas inside molecular clouds, it is now understood, is actually quite turbulent. Gas motions, there's bulk motions of different parts of the cloud. This too contributes to the support of the giant molecular cloud against its own self-gravity. And indeed, their self-gravity can be quite large. They have masses of 1,000 to 10 million times the mass of the Sun. You can see herein part of the challenge of forming a star. The starting point is about as unstar-like as you can imagine. The sizes are measured in parsecs, not in tens or thousands of kilometers. The masses are measured in thousands to millions of times the mass of the Sun, not in units of the mass of the Sun. The temperatures are 10 or 30 degrees Kelvin above absolute zero, not thousands to millions of degrees Kelvin. And the densities are only 10 to the 4 to 10 to the 6 atoms per cubic centimeter, not densities more like 10 to the 24 and up inside of real stars. So a molecular gas cloud has a long ways to go before it becomes a star. And that's actually part of what makes forming stars so difficult. They have a long, long ways to go from the raw material to the final product. These giant molecular clouds are held up against gravity by the combination of gas pressure, magnetic fields, and turbulent motions, but they're only just held up. They are what we would refer to as marginally stable against gravitational collapse. If gravity becomes slightly larger than the internal pressure, the entire cloud is simply going to collapse on itself. The collapse will proceed faster than the internal gas pressure, at least initially, can respond to the change. These are systems that are far out of hydrostatic equilibrium. There are lots of ways to trigger the collapse of a giant molecular cloud. One way is for two clouds to simply bump into each other. They orbit through the galaxy, they're big, they're orbiting around the galaxy, and occasionally they're going to bump into each other. At the point of collision, that produces an overpressure. That overpressure is, if it's inward pointing rather than outward pointing, will actually tip the balance in favor of self-gravity, and the star will begin to collapse. Another way to tip the balance in favor of gravity is to have a large overpressure strike the cloud in the form of a supernova explosion blast wave. Supernovae, as we'll learn later in this course, are the explosions of either very massive stars at the end of their life or thermonuclear explosions of white dwarfs and binary systems. These shock waves, really blast waves, going out through the interstellar medium, if they run into a giant molecular cloud, can overpressure it and cause it to initiate collapse. Finally, the galaxy in which these giant molecular clouds reside is crisscrossed by spiral arms, as we're going to learn in the next unit of this course. These spiral arms are places where the external gas pressure is actually slightly elevated. Two things can happen as a giant molecular cloud passes through a spiral arm. If the spiral arm represents a region of high interstellar gas pressure, that additional external pressure can trigger a collapse, or because orbits tend to crowd together as they pass through spiral arms, it can actually become a place where you are more likely to have one of these cloud-cloud collisions. That's the first way we described to trigger a collapse. Which way a collapse is triggered really has more to do with the basic statistics of how a particular galaxy, this whole system of stars, gas, and dust, goes about forming stars on the large scales. But however it happens, once the collapse starts, the process proceeds fairly rapidly. As a giant molecular cloud collapses, it not only collapses, but it also begins to fragment. These systems are very turbulent. There's gas moving in very different ways. You don't want to think of these as sitting there kind of stably balanced on the razor's edge. These are very dynamic systems, as we've learned in the last few decades. And so as a consequence, when the cloud begins to collapse, it doesn't just simply fall down into a single point, but fragments up into a number of small, dense cloud cores. Giant molecular clouds are clumpy. This typical clump size is about 1/10 of a parsec, and the clump masses are a few times the mass of the Sun. Notice this is important. We see in this picture over here on the right of Thackeray's globules in the star cluster IC 2944, this gorgeous Hubble Space Telescope picture. The bright red background you see is ionized gas lit up and fluoresced by hot stars in the region, but the dark clouds are little fragments of molecular gas clouds. You can see that they're irregular in shape. The masses of these are a few times the mass of the Sun, and they're a fraction of a parsec across. These are very suggestive because, unlike the giant molecular cloud complex in which they resided, these smaller gas clumps are roughly stellar in scale, and these are eventually the pieces out of which one or perhaps more stars will form. The very highest clump density clumps, like in this group in Thackeray's globules, are going to be the most unstable. They're going to collapse first, and they're going to collapse fastest. The collapsing cores have masses comparable to stars, so this is going to be the starting point of star formation. We're going to follow one of these dense cloud cores as it begins to collapse. They collapse from the inside out. The inner, denser portion of the core collapses first, and the outskirts kind of follow along a little bit later. The cores start out as relatively low density and transparent to light. If photons are produced in the hot gas in the interior, these photons can actually work their way, random walk their way out of the cloud, leaking out, carrying away heat, causing that gas, which is being heated by compression, to cool. If the gas cools by radiating away energy, they can't build up pressure to counterbalance gravity, and so the core keeps on collapsing. That these clouds are leaky to photons hastens their collapse because it makes them unstable. These are not in hydrostatic equilibrium. Far from it. They're losing energy faster than they're getting it back by compression, at least at this phase. The core density is going to continue to collapse and continue to rise until the rules change. And the rules change when the core becomes sufficiently dense that it starts becoming opaque to light. Now the photons that used to just leak out and carry energy away get trapped inside the core. As they're trapped inside the core, those photons now go into heating the gas. As they heat the gas, the pressure begins to build up faster and faster. In other words, now the collapse actually leads to an increase in pressure, and the collapse begins to slow a little bit. It reaches the point where you begin to form what we call a hot protostar at the center. This hot protostar is the dense, opaque, and now growing increasingly hot core of this molecular cloud. It's embedded deep inside this larger clump that's collapsing away, slowly building up as matter and gunk rains down upon this inner protostar. It's slowly growing in mass. So the protostar phase is the phase that is characterized by very rapid growth of the mass of the central hot core by the steady accretion of gas. These are not yet, however, a system in hydrostatic equilibrium. They're still growing in mass, and gravity is still staying greater than the internal pressure. While the pressure is building up as they collapse, gravity is getting stronger as more mass rains down on top of it. This gravitational contraction, as the mass grow, accelerates the process of heating the protostar. So it's kind of a runaway process. Each thing that the protostar does, everything that happens to the protostar, is making it hotter, denser, and smaller, and it's pushing it down into smaller states. The protostar phase is very, very short. This all happens really rapidly. The time scale, we think, is between anywhere from 10,000 to 100,000 years. What we will end up with is a protostar buried and deeply embedded inside the dust and gas cloud, and very, very hard to see. An example is shown over here on the right-hand side of the screen. In the upper right-hand panel, we see a visible light photograph of one of these collapsing cloud cores. And what we see in visible light is we see the background of stars, and then we see a place that looks like a hole in space. That hole is just the dense collapsing cloud blocking the starlight from behind it. And so we're seeing it as a cold, dense black cloud. If, on the other hand, inside the square, I shift into infrared light can leak out of the dusty core, I see buried deep inside that cloud core a very, very hot, very, very bright protostar. It's not yet in hydrostatic equilibrium. Pressure cannot yet equal the force of gravity, and so it continues to collapse, continues to grow in mass, and continues along, growing hotter and denser and growing in mass. This protostar phase, however, comes to an end when it stops accreting matter. As it stops accreting mass, the mass stops growing, and now the protostar, to all intents and purposes, is about as massive as it's ever going to get. In reality, it will grow a little tiny bit, but the mass growth is going to fall off dramatically. Still thin. We're now going to add little bits and dribbles, but by and large, it's about as big as it's going to get, except for a small bit. Now, it begins to approach hydrostatic equilibrium. Because its mass is as big as it's going to get, the gravitational contraction, the gravitational energy content is now set. As it collapses, it heats up. As it heats up, the pressure grows until you reach the point that basically the protostar stops growing. It stops growing when its luminosity, the amount of energy it's losing from its very, very hot photosphere, becomes high enough that the pressure of the light, the pressure of the photons, begins to push away the remaining infalling gas. You still get a little bit of remaining gas and dust around. It will settle down into a disk that will orbit around the equator of the small spinning protostar. The protostar settles down and achieves hydrostatic equilibrium. It's now a well-defined, separate, hot, dense entity in hydrostatic equilibrium. It's no longer a protostar, But it's no longer a star either, and it achieves an intermediate state we refer to as a pre-main sequence star. The pre-main sequence phase is a time when the star is no longer growing in mass. It's in hydrostatic equilibrium, but is not yet in thermal equilibrium. This means that it's actually losing more energy, and it has no source of energy to make up for that, or the source of energy it can tap is not able to make up for its losses. Pre-main sequence stars evolve at a near constant mass from this point on, but are still surrounded by these disks of gas and dust, as shown in this artist's conception of a pre-main sequence star. Notice now that the disk is actually separated from the pre-main sequence star. The mass growth now has fallen off to but a very faint dribble. The central pre-main sequence star is gaining energy. The source of energy is gravitational contraction through the Kelvin-Helmholtz mechanism. We met the Kelvin-Helmholtz mechanism a couple of lectures ago when we talked about how long the sun can live. And we learned that the Kelvin-Helmholtz mechanism could only provide enough energy to provide for the energy needs of the sun for only about 30 million years. That wasn't enough for the billions of years of the sun's life. But that doesn't mean that the Kelvin-Helmholtz mechanism does not occur at some point in a star's life. And indeed, the Kelvin-Helmholtz mechanism is the most important, in fact, the only source of energy, or the primary source of energy, during the pre-main sequence phase. So the pre-main sequence phase, because it's powered by Kelvin-Helmholtz, not surprisingly, we would expect is going to be relatively short-lived. As the radius of the star, r, shrinks as the star contracts, we're going to find that about 50% of the energy generated by the Kelvin-Helmholtz mechanism is going to go into photons, making up for the luminosity of the star, and the other 50% is going to go into making the interior of the star hotter. As the gas begins to compress, it begins to heat up. And now we're at the point where we're about at the crossroads in the star's formation. At this point, it's not yet a star, but it's on its way to being a star. The next step is it has to reach a point where it's hot enough in the interior to ignite hydrogen fusion. And those are the stages that we're going to examine in the second part of this lecture.